Greetings and welcome to the Chemistry 221, the determination of an empirical formula lab. This lab will provide experience with how to not only go from grams to moles, which is a big part of it, but how you can use those moles to find first the empirical formula, which is the smallest whole number ratio of atoms. And from there, you can also go on to the molecular formula, which is kind of the desired thing usually, but the empirical formula is an important first step as you go through this. So without further ado, let's get into the lab. And again, like I said earlier, the goal of this lab is to become more familiar with the concept of the empirical formula. And I'm going to abbreviate that as EF sometimes for obvious reason. It's kind of a strange thing. But anyway, empirical formulas are just the smallest whole number ratio of atoms in a molecule. And if you look in the lower left-hand corner there, there's a table. And the column that I just put the arrow to, all of those are empirical formulas. So if you look at the first one there, hydrogen peroxide, in the quote-unquote real world, hydrogen peroxide has 2 hydrogens and 2 oxygens. The empirical formula would be the smallest whole number ratio of atoms. So if you divide both of the 2's in H2O2 by 2, you get 1H1O or HO. So HO would be the empirical formula for hydrogen peroxide, which is actually H2O2. Having a whole number is important. So you can see on the next example, water, H2O, you can't make that 2-to-1 ratio any smaller without getting into fractions. So H2O is both the empirical formula and the molecular formula for water. And you can see the other examples down there. Again, in this area, you don't want to use fractions. So if you can't break it down any further into whole numbers, you just leave it alone like is in water. The empirical formula and the molecular formula then, as you can see, sometimes they are the same and sometimes they're different. But there's several different ways to get to empirical formulas, and that's what we're going to focus on in this lab. And then from there, it's not too difficult usually to go from empirical formula to molecular formula. Most of the time in ionic compounds, the empirical formula and the molecular formula are the same. So as an example of an ionic compound, which again has a positive cation and a negative anion, you could have something like NaCl, or that would be sodium chloride. You could also have KNO3, potassium nitrate. Both of those, the empirical and molecular formulas are the same. It's mostly for covalent compounds, and that's what all of that table is in the lower left-hand corner, where a lot of times the EF and the MF are different. So as we talked about earlier, water is the same EF and MF, but hydrogen peroxide is obviously different. If you do want to make sure that your empirical formula is the same, or for that matter different than the molecular formula, you need a molar mass calculation. That's like a separate experiment. It's not hard to do, but with that number, you can too convert an empirical formula to a molecular formula. The first way we're going to look at how you can get an empirical formula is from mass data, all right? And what this usually means is this is something done in the lab where you put like so many grams of element in, and it reacts with so many grams of a second element to make a compound. And using those mass values, you can go mass to moles and compare them to find the empirical formula. Let's look at an example of how this works. In the problem right there, it says we have a 25-gram sample of calcium, and it's reacting with excess chlorine, which means we have more chlorine than we know what to do with, and it creates a compound with 69.224 grams solid. And it says determine the empirical formula of the resulting calcium chloride compound. Okay, so what this means is that the 25.000 grams, all of that was used up. And because the compound, the white solid, has a total of 69.224 grams, then that means that all of that 25 grams went into the 69.224 number. That also means, which is important for us, is that to find the grams of chlorine that reacted, you take 69.224 and subtract 25 from it. So in this first part of the problem, an empirical formula is always a mole ratio. So if you have something like 25.000 grams, let's right away turn it into moles. So you can see there we divided by the molar mass of calcium, the number on the periodic table. Calcium is number 20 on the periodic table. So if you look up and you look up the right version, then it goes to 40.078 grams per mole. I used 5 sig figs because we're putting 5 sig figs in. This comes out to be the 0.62378 moles calcium number. And then to find the chlorine, we take the difference between the compound, 16.224 grams, and the calcium, 25.000 grams. Remember, the 69.224 gram number has only calcium plus chlorine. So if we subtract the calcium from it, the remainder, which is the 44.224 number, that's the grams of chlorine in the compound. So we use the difference in masses to find the grams of chlorine in this case, which is very common in these kind of problems. And from there, you can take the grams of the chlorine, turn them into moles, again using the molar mass of the chlorine number 17 on the periodic table, 1.2474. So now we have the moles of calcium and the moles of chlorine. And you could write this as Ca 0.62378, Cl 1.2474, but man, that's a messy formula, and chemists are anal retentive too. We don't like messy things. I don't know. So to go from these rough mole values to a nice whole number value, you divide both of those numbers by the smaller number. And in this case, 0.62378 is certainly smaller than 1.2474. You're actually dividing both of those numbers by 0.62378 because 0.62378 divided by itself is just 1. So that means we have 1 calcium. And as you can see there, 1.2474 divided by 0.62378 is about 2. So that means 2 Cls. So 1 Ca, 2 Cls. This is CaCl2. This is calcium chloride. So using these mass values, we turned grams into moles. We then compared the moles. You divide by the smaller one because you always want whole numbers. It makes your life easier to get CaCl2. This is an example of how to find an empirical formula from percentages, and it's very common in the chemistry world to send your sample to a type of analysis where the percent by mass version comes out, and that's what we're looking at here. Like with the last examples, we want to turn somehow mass into moles and compare the moles. The only trick about the percentages is that what I would do is you can assume 100 grams total, so the percentages become the grams to moles, compare, you got the empirical formula. So anyway, in this problem, we have a compound that's 83.01% potassium and 16.99% oxygen. Let's calculate the empirical formula of this compound. Cool, no problem. So again, like it says in their beginning, what I would do is assume 100 grams total. If you have 100 grams total, that means then that 83.01% K becomes 83.01 grams of potassium. And the same thing for the oxygen, 16.99 grams of oxygen from 16.99% oxygen. And you could assume any number you want. For example, some people like using just 1 gram. That's fine. You'd then have 0.8301 grams K and 0.1699 grams of O. I am a 100 gram person, so that's what I'm doing here. But if you want to use 1 gram, that's cool too. From this point, it's pretty chill. Now you take grams to moles like we did in the last example, compare the moles to find the empirical formula. And remember, when you compare moles, you divide by the smaller number. Here's what this part looks like. First, here's the grams to moles. So the 83.01 grams of potassium turned into 2.123 moles of K, 16.99 grams turned into moles, 1.062 moles of oxygen. You can probably tell that's almost a 2-to-1 ratio, but to make sure, smaller moles on the bottom, bigger moles on the top. So 2.123 divided by 1.062 is what we're going to do. If you do that, that ratio comes out almost exactly to 2. And remember, we did divide 1.062 by 1.062 as well. That gave us the 1. Anyway, in this example, then you've got 2 Ks for every 1 O. K2O, potassium oxide, is the problem. So we've seen now 2 ways to get empirical formulas. The first way was using mass values, which is usually done in the lab. This version here with percentages is usually when you send a sample away to a type of device that measures mass percentages. They'll send you back the numbers. You can figure out the formulas. Both ways come in really handy. If you have to determine the mass percent of an element in a compound and you know what compound it is, it's not too bad. The formula I like to use is mass percent equals mass of the element divided by total mass of the compound times 100%. And what I do in this compound is I always assume that there's 1 mole total. If you have 1 mole total, then the total mass of compound will literally be just the molar mass. And on top then you'll put how much of that element went into the molar mass calculation to figure out mass percent. And if that was about as clear as mud, I understand. Let's look at an example. So here's a problem. Find the percent chlorine and percent chromium in chromium 3 chloride, CrCl3. Okay, no problem. So what we're going to do is we're first going to find the molar mass of the chromium 3 chloride. So on the periodic table, look up a chromium and chlorine, multiply the chlorine by 3 because of the 3 in CrCl3, add them together to give the molar mass. So here's what I did for that. Chromium is about 52 grams per mole, chlorine about 35.45 grams per mole, and there's 3 of them. If you add all of that together, you get 158.35 grams per mole. That's the molar mass of chromium 3 chloride. And we're going to put that 158.35 number in the denominator when we figure out percent elements here in just a second. Percent element, you put the molar mass in the bottom, and on top you put how much of the element was used. So for example, for chromium here, we had 1 chromium, and so that's the number that was put right there. All right, so I literally just put the 52 down there and divided by the molar mass. This compound is 32.84% chromium. Now for chlorine, it's the same idea, but remember we multiplied chlorine's mass by 3 because of the 3 Cl's. And we want that whole thing in the top part there when we figure out percent chloride. So for percent chloride, 3 times 35.45 divided again by the molar mass of the whole thing times 100%, 67.16% chlorine. And if we sent this compound away for analysis, we would hope to get 32.84% chromium and 67.16% chlorine. Now, we can make sense a little bit if these values are reasonable. If there's only 2 elements, then they'll add up to 100%. So 32.84 plus 67.16 is 100%. Cool, that's good. If you had 3 elements in a compound, then you'd add all 3 of them together, and that should equal 100%, etc., etc. If you don't get 100%, it might mean that your math is kind of weird. Also, if there's only 2 components, and you have the first one, say the percent of chromium from earlier, 32.84%, you can find the second percent element by 100% minus 32.84. So we could have also found the percent chlorine by going 100% minus 32.84, and that will give the same answer. Sometimes that's a handy way to do things as well. So finding a percent by mass of an element in a compound is not too bad. Molar mass on the bottom and how much of the element goes into it on the top. Once in a while, it will be nice to know the molecular formula. This is especially important when you have compounds made of covalent bonds, so nonmetals and nonmetals. And it's pretty easy to convert an empirical formula to a molecular formula. I'd also like to show you an example of this one here. All right, so in this particular problem, we have a compound with an empirical formula of CH2. And we do a separate experiment on this compound and find that the molar mass, 112.2 grams per mole. We can use this information to calculate the molecular formula of the compound. But before we do that, I want to remind you that H2O2 was hydrogen peroxide, and we saw that the empirical formula was HO. So again, H2O2 would be the molecular formula, what it quote-unquote looks like in the real world, but the empirical formula is HO, 1 hydrogen to 1 oxygen. Now, the reason this is an empirical formula lab is that you can get that 1-to-1 ratio like that. You can get it from masses. So like we saw the example of calcium and chlorine, you could do this kind of thing with hydrogen and oxygen, and that would give you the HO empirical formula. You can also use mass percentages from another experiment to find that it's HO. So HO is usually like the first step of finding what a formula is. Now, hydrogen is about 1 gram per mole, and oxygen is about 16 grams per mole. So if you take hydrogen at 1 and add it to 16 for oxygen, that means HO has a molar mass of about 17 grams per mole. And when you think about what H2O2 hydrogen peroxide would be, it would be 2 hydrogens at 1 each and 2 oxygens at 16 grams per mole each. This is about 34 grams per mole. And 34 divided by 17 is 2. And that's important to us here because HO taken twice is what hydrogen peroxide is. So notice that if you have an empirical formula, then it's an empirical formula taken so many whole numbers that will allow us to find the molecular formula. And the goal is, like in H2O2, the goal is to find this number 2. And what people will do is they'll take the molar mass of the whole compound, 34, divide by the molar mass of the empirical formula, which is 17. 34 divided by 17 is 2. That's how you get this ratio. And you take that ratio, multiply it by the empirical formula to get the molecular formula. So in this compound, the 112.2 number, that's like the 34 number above. All right, we've got the molar mass of the whole thing. And CH2 is like the HO right there. All right, that's the smallest whole number of the empirical formula. So you can probably see that what we need to do is we need to take our empirical formula and find out the molar mass of it like we did with HO. So for CH2, what we're going to do is we're going to add up a carbon and 2 hydrogens. And when you do that, you get 1 carbon is about 12 grams per mole, 2 hydrogens, 2 times 1.01. Molar mass is about 14.03 grams per mole. And this number, the 14 number, is the equivalent to the 17 number up here I was babbling about. So what we did then to find the ratio of 2 is we took the molar mass of the whole thing, which was 34 for H2O2. We divided it by the 17, the molar mass of the empirical formula, to get this number of 2. What we want to do in our problem now is take 112.2, the molar mass of the whole thing, and divide it by 14.03. And we're always going to get a whole number there. We're going to take that whole number and multiply it by CH2 to get the molecular formula. So 112.2 divided by 14.03 is almost exactly a factor of 8. That's the ratio. Now for hydrogen peroxide, the ratio was 2. 34 divided by 17 was 2. Here 112.2 divided by 14.03 is 8. Doesn't matter what the ratio is, that's what you multiply the empirical formula by. So CH2, we need to take it 8 times. So we multiply 8 by 1 to get 8 carbons, 8 times 2 to get 16 hydrogens. This formula, molecular formula now, C8H16. Pretty cool. So again, take the empirical formula's molar mass, compare it to the molar mass of the whole thing. You're going to get a whole number. It was 2 for hydrogen peroxide and 8 for this example. Whatever that whole number ratio is, multiply it by the empirical formula. The molecular formula will be yours. This is a problem where we're going to find not just the empirical formula, but the molecular formula as well. This is kind of like the whole shebang here. We're putting it all together. Woohoo! So let's use this information to find the empirical and the molecular formulas of this compound dimethyl ether. And if you read through this information, the dimethyl ether here has carbon, it has hydrogen, and it has oxygen. And with those percentages, and the molar mass of the whole thing is 46 grams per mole. So what we're going to do in this problem, we're first going to find the empirical formula of the CHO compound. Sometimes those are called hydrocarbons. You can call it whatever you want. We're going to find the empirical formula of the hydrocarbon, and then we'll compare the empirical formula to the molar mass, 46 grams per mole, to find the molecular formula. So like before, assume 100 grams, turn grams into moles, and compare the moles to find empirical formula. So the first part, let's take those percentages, turn them into grams. So 52.14% becomes 52.14 grams of carbon. Turn it into moles to get the 4.341 number. We'll do the same thing with hydrogen and the same thing with oxygen to get those numbers. Now there's 3 mole values here, but again, you want to divide all of them by the smallest number. 2.171 is smaller than the other 2 numbers, so that's going to be on the denominator, and we'll put the other ones in the numerator. So 2.171 divided by itself is just 1. We're going to do the same thing for the carbon and the hydrogen. And when you do that, the carbon to oxygen ratio then comes out to be 2, and the hydrogen to oxygen ratio comes out to be 6. You're going to have 6 hydrogens for every oxygen. The empirical formula then will be C2H6O1, or the empirical formula is just C2H6O. So no big deal. So the same kind of thing. This had 3 elements, but divide by the smallest one. This came out to be a 1 to 2 to 6 ratio, or C2H6O, no problem. Now notice that we haven't used the 46 grams per mole number. We're going to use that in the next step when we go from the empirical formula to the molecular formula. In the last slide, we found the empirical formula was C2H6O. We want to use this formula and the molar mass of 46 grams per mole to find out what the molecular formula is. And like on the example we did earlier, we're going to find the empirical formula's molar mass, compare it to the molar mass of the whole thing, get a whole number. That times the empirical formula will equal the molecular formula. So let's find the molar mass first. This thing is C2H6O, so there's 2 carbons, there are 6 hydrogens, and 1 oxygen, and this number comes out 46.08. But wait, the molar mass of the whole thing, 46 grams per mole, not as many sig figs. No problem. Let's continue going. So in this case, you can probably see that the ratio is just 1 to 1. 46 and 46.08 are pretty close to each other. So that means your empirical formula times a ratio of 1 is basically just itself. So C2H6O in this case is not only the empirical formula, it's also the molecular formula. Remember we saw water earlier, and water was H2O, and you can't break H2O down to smaller whole number values. Well, this compound dimethyl ether is the same. You can't break C2H6O down to smaller whole numbers. So this is another example of when empirical formula and molecular formula are the same. So if your ratio between the molecular formula and the empirical formula does come out to be 1, it's okay. That just means empirical and molecular formulas are the same. A lot of times though, as we've seen already, you'll have have different ratios like 2 or 6 or whatever, just multiply whatever that is by the empirical formula to find what the molecular formula is. But I wanted to throw this out as an example of what you could see. In this lab, we're going to explore the methods that chemists use in order to find the empirical formula for what's called a copper chloride hydrate. Now you can see down there in that little formula, there's an X by the copper, a Y by the chlorine, and a Z by the water. Now all those little letters, X, Y, and Z, those are mole ratios, and the goal for you is to find what they are. Now copper is a transition metal and a variable charge metal, so it's not necessarily certain what its charge is going to be, and that will reflect itself in how many chlorides adapt. So for example, if you had a copper +1, you'd have 1 -1 chloride. If you had a copper +2, you'd have 2 -1 chlorides, etc., etc. So that's how you can find out what's going on there. Now, in a hydrated compound, different amounts of water will connect themselves to, in this case, the copper chloride. You might have 2 waters, you might have 5 waters. There's all different variations of it. The hydrated compounds are usually quite beautiful, and in this lab, as you'll see here in a little bit, the copper chloride hydrate we're using is quite beautiful in my opinion. Now, of course, I need to get out more. I'm a chemist, etc., etc. However, I think you'll find that they're a lot more spectacular with the waters than without, as we'll see here in a little bit. So to do this, we're first going to dehydrate the copper chloride hydrate. And what that means is the waters will be kicked out, all right? And we'll be able to isolate by a difference in mass how much water was lost, all right? So if your sample went from, say, 3 grams to 2 grams after this dehydration heating process, that would mean you'd have 3 minus 2 or 1 gram of water in your sample, stuff like that. Once you have the copper chloride, then we can actually add some zinc metal to it. And zinc metal reacts with the copper ions to make copper metal, which is elemental copper, copper by itself. And you'll also make some zinc chloride along the way, which by the way is ZnCl2, and you might need that for a post-lab question, hint, hint. This is a really fun lab. You start off by using a Bunsen burner to heat the copper chloride. The water comes off, you see lots of color changes. You then take the copper chloride that's been dehydrated and add water back to it. You add the zinc metal, and there's some pretty fantastic transitions. You use some vacuum filtration to get the water off of the copper chloride once you've made it and the pure copper. It's pretty cool. Anyway, just get ready. This is kind of a cool lab. At any time, if you have questions, let me know. You're going to end up with grams of pure copper, grams of the water from the dehydration, and from the difference in mass, you'll be able to find the grams of chloride. And from all of those, you'll turn them into moles. You'll compare the moles to find the X, Y, and Z values in that formula, and that'll be how you find the empirical formula. And along the way, we'll also figure out percent copper and percent chloride based on the mass percents you have. And we'll even talk about what's called a theoretical yield and actual yield, which is what chemists use to figure these things out. And the percent yield will tell you how efficient your reaction was, stuff like that. So it's a pretty cool lab. It introduces some real powerful tools for chemists who want to figure out how much products are made, stuff like that. Okay, at this point, I think it's time for a video. Again, if you have questions on anything, just let me know. I'm happy to help. Good luck with your lab.